Hello, and welcome to the video accompaniment for Chapter 12, Section 1 of our text. There'll actually be a couple videos for this section. In this first video, what we're going to do is just talk about some definitions and give some examples of definitions. So this is a new subject with a lot of different terms and definitions that we need to get through before we can start working with these things. And so that's the goal of this video. So we're going to see terms, we'll define what a graph is, we'll talk about subgraphs, and these different varieties of subgraph, proper, spanning, and induced. Remember, with sets, we could have just a regular subset or a proper subset. With graphs, it's a little bit, we have more information about our sets, and so we'll be able to define different sorts of ways one graph can sit inside of another. That's what these three terms will refer to. What's a vertex? They sometimes go by the terms nodes or points, depending on what field you're working in. Edges or links, lines, arcs. What it means for two vertices or edges to be adjacent. What it means for a vertex to be incident with an edge. What a neighborhood is. What the degree of a vertex is, and what it means for a vertex to be R, or for a graph to be R regular. So we'll go through all these terms. I'll also motivate the definition of a graph and kind of give you an idea of why one might work with a graph or where one would see these in the real world. All right, let's get started. So first off, what is a graph? Well, a graph is a set of vertices together with a set of edges connecting pairs of vertices. And that's all you need to know about graphs. Just kidding. Let's go through an example of a graph and a way to represent it. So this is what a graph is. It's a set of vertices together with a set of pairs of vertices. So what's a vertex? Well, it could be literally anything. Just some set of objects. That's all a vertex is. It's just something. It's some object. And if we collect all the objects we're going to be dealing with, that's our vertex set. So this is our vertex set is A, B, C, D, and E here. And then our edge set, edges are pairs of vertices, unordered pairs of vertices, in the case of a simple graph that we're dealing with here. So here this is telling me that A and B are connected, B and C are connected, C and D are connected, E and A are connected, and C and E are connected. Notice these are unordered pairs. So saying A and B are connected is the same thing as saying B and A are connected. I don't need to list that twice. There is a related concept to a graph we'll talk about at the end of this video called a digraph or directed graph, where we do want some directionality for our edges. So a vertex A goes to vertex B, but maybe not the other way around. So we'll talk about that at the end, but this is really what a graph is just this. Of course, this doesn't, this might be the graph. So this is how we can represent it. G equals VE. It's just a pair of sets, one of vertices, one of pairs of vertices. But how a graph is usually represented is visually. And so here I'll draw this graph here on this slide. So I'll just put a point down or a little circle for each of my 5 vertices, and I'll label them with their names, A, B, C, D, and E. And then how do I represent these edges? Well, A and B are adjacent to each other, or they're connected. That edge appears there, and so I'll draw a line between vertex A and vertex B. B and C are connected, so I'll draw a line segment between those two vertices. C and D are connected. E and A are connected. And C and E are connected. And so this is one way to represent my graph G, is through this visual diagram. And actually, if you draw a diagram like this with all the vertices labeled, this is a perfectly fine way to define a graph, is just by drawing a diagram like this. And labeling the vertices. Okay, so this is what a graph is. Let's start getting into some terms. The order of a graph is the cardinality of its vertex set. So cardinality of V is, there are 5 vertices here. This is the order of the graph. Since a graph is 2 sets, right, we're going to have to talk about the cardinality of the vertex set, the cardinality of the edge set. So the order That's the cardinality of the vertex set. The cardinality of the edge set of a graph, this is called the size. So here we can count up how many edges there are. 1, 2, 3, 4, 5, or count it here, 1, 2, 3, 4, 5, and there are 5 edges here. Now, this example, I have the same number of vertices, or the number of vertices is the same as the number of edges. That doesn't always have to happen. Nevertheless, we call this the size of G. So that's something to get used to. Order means number of vertices, size means number of edges. So I've already used this term adjacent. So whenever two vertices are connected with an edge, so if there's an edge in the edge set that contains those two vertices, we say that those two vertices are adjacent. So for example, the vertices A and E here are adjacent vertices. A and E are, that's an example of an adjacent, adjacent vertices are adjacent. At the same time, edges can be adjacent to each other. So while vertices are adjacent if they are in the same edge, right? If there's an edge between them, two edges are adjacent if they share a vertex. So for example, AB and BC are adjacent edges. So vertices can be adjacent, edges can be adjacent if they share a vertex. Now, sometimes we don't like drawing these set braces around my vertices all the time when I'm referring to an edge. So sometimes, even though there isn't an order, we'll list edges as strings. So we might have also said AB, the edge AB, and the edge BC are adjacent. So sometimes we will drop the set braces and just write it as a string, write each edge as a string like that. So that's okay to do. Notice that in the case of a simple graph like this, the edge AB is the same as the set as the edge BA or CB. When we have directed edges, it won't quite be the same, right? There'll be some direction to it. But for now, we can do that. Okay, so that's adjacent edges, adjacent vertices. And then what do we say when an edge meets a vertex? We say that that edge is incident to the vertex. So for example, I'll write this in green. How about the edge AB is incident with vertex A. So that's an example of an incident pair or an edge being incident with a vertex. And so we say that just when there's an edge coming off of the vertex. So just a point of, I guess, nomenclature here, right? A singular, right? An element of the vertex set, singular is a vertex. And when we're talking about a collection of these objects, they're called vertices. So vertex singular, vertices plural. And I think that's all I want to talk about on this slide. Let's go to the next slide where we'll talk about subgraphs. So just like a set can be a subset of another set, right? So we can think of like a set containing another set in some way. We can think of a graph containing another graph in some way. So what I'm going to draw here, are 4 graphs, and I'll sort of pick out what the relationships are between them. So I'm going to call this one G. And like I said, it's perfectly fine to define a graph by just drawing it. Sometimes a graph will be sort of too big to do this, and there we'll want to define what the vertex set and maybe give some rule for how two vertices are adjacent to each other. But for some small graphs that I'll put here, it's enough to just draw them and label the vertices. So what am I going to call these? U, V, W, X, Y, and Z. So that's my graph G. We can pick out its vertex set, right? So it's a bit of notation, right? So if I write V of G, that means the vertex set of G. And give it like a function on the graph that returns its vertex set. So in this case, V is the V of G is the set U, V, W, X, Y, and Z. And then similarly, I can write E of G to mean the edge set. And I'll draw these as just without the set braces. So here UV is an edge, UW is an edge, VW is an edge. Let's see, VX, WX, WY, and XZ are all the edges. And so here's my formal definition for G. Along with this, I'm gonna draw a graph G1. And I'm going to use the same vertex set here, or at least a subset of the vertex set. And then again, we have X, Y, and Z. And this one will be a little bit different. U, V, W, like that. VX, XY, WY. And then how about Z up here? So it's very similar to G, but it looks like we dropped an edge. Let's get the other two in here that I want to talk about. G2, W, X, and Y. So there's the names of my vertices and how are they connected. I guess I'll mention a quick term right here while I'm drawing these. A graph doesn't necessarily have to have any edges. It could just be a set of vertices with an empty edge set. In that case, we say it's an empty graph on that number of vertices. And there's only one way to do that. Just draw the vertices with no edges. U, V, X, and Z. What else do I want? Okay, I want those, that one, and that one. U, V, X, and Z. So here I have 4 graphs for you. And I'd just like to talk about containment of these things. How does one thing contain another, and in what ways? So each one of these, notice here, my vertex set is the same as the vertex set of G. So I can write, let me use gold for this, the vertex set of G1. We could list those, but it is the same. So I'll say equals, it's the same exact set as the vertex set of G. However, we're missing an edge. So the edge set of G1 is a proper subset of the edge set of G. And so when this is the case, whenever we can delete vertices or delete edges to obtain a new graph. So like to get from G to G1, I could have deleted the edge WX. And so we say G1 is a subgraph of G. And we can write that just using our normal set symbol. G1 is a subgraph of G. And in this case, we can say more. We can say that G1 is a proper subgraph of G because it's not equal to G, that we deleted at least one edge or we deleted at least one vertex. In the same sense, G2 is a subset of G. In this case, we've deleted some vertices as well as some edges. So we took away the vertex U, we took away the vertex Z to obtain G2, and we also took away the edge WY. And so again, G2 is a proper subset of G. Notice here G2 is not a subgraph of G1. So why is G2 not a subgraph of G1? Well, because it has this edge WX in it that G1 does not have. So in order for a graph to be a subgraph of another one, either the vertex set or the edge set or both have to be a subset of the original graph. G3, on the other hand, that is a subgraph of G, U, V, X, Z. I can sort of see it inside of my graph G like that. So G3 is a subgraph of G. But we can get more specific about how the graph G contains these other graphs. So what do I mean? Well, right, since we have these two sets that make up a graph, we can talk about containment in those ways. So for example, G1 here, the vertex set of G1 is equal to the vertex set of G, but it's missing some edges. So in this case, we say that G1 is a spanning subgraph of G. So this means that G1 is a spanning subgraph of G. So spanning just means that the vertex sets are the same, but maybe we have, you know, proper subset in for the edge sets. But spanning just that the vertices are the same. So I don't see any other spanning subgraphs here because this vertex set is different than the vertex set of G, and these are all different vertex sets. So that's the only spanning subgraph here. We can also talk about this idea of an induced subgraph. So an induced subgraph means the vertices aren't necessarily the same, but the edges should be consistent among the two graphs. So what does that mean? It means, so let me pick one out here. G3 is an induced subgraph of G. So what this means is that if two vertices of G3, so my vertex set of G3 are the vertices U, V, X, and Z. Notice that's a proper subset of G. And notice further that, so if I take these vertices and I look at their adjacencies in G, so let me point out the adjacencies. So U and V are adjacent in G, Vx are adjacent in G, and Xz are adjacent in G. And that's all the adjacencies between U, V, X, and Z inside of G, right? We see U is not adjacent to X in G, U is not adjacent to Z, Z is not adjacent to V. So the list of all the adjacencies here in G, all the edges, just using these vertices, it's the same as over here, UV, VX, XZ. I didn't have to delete any edges directly to get to G3. Notice I deleted vertices, but when I took those vertices out, well, I couldn't very well keep the edges that were incident with them, right? Those have to go along with it. When I delete a vertex from a graph, all the edges incident with it also go away. And so really, I can say here an induced subgraph, so if one graph is an induced subgraph of the other, that means it was obtained from the original graph by deleting some vertices, but not necessarily deleting any edges. And in fact, we don't want to delete any edges directly, just those ones that came along with the vertices we deleted. So that's what an induced subgraph is. Whenever we have an edge over here, we have an edge over there, and vice versa. An edge over here transfers to an edge here, and it also preserves the non-adjacencies, right? Like UX was not an edge over here, and it's not an edge over here as well. All right, so that's proper subgraph, induced subgraph, spanning subgraph are different ways to talk about one graph containing another graph. So one might wonder, why do we have this definition for a graph? Why would we care about having vertices and edges between vertices? Well, you'll notice in this definition, right, it's very abstract. It's almost as abstract as the definition of a set, as just a collection of objects. A graph, same type of deal. It's a very abstract concept. And that's sort of the beauty of it, is it can, because it's so abstract, this high level of abstraction leads to being able to apply this to a lot of different situations. So anytime we have a collection of objects with some way to think of two objects being related to one another, we can form a graph out of that. And we have this visual representation of it, and any theorem that we've proved about graphs will apply to that situation. So that's the idea, is we'll prove a bunch of theorems about graphs as a structure in and of themselves, and then that can be applied to any situation that calls for a graph. So I'll just talk a little bit about the history and some applications of graphs here. I have this first one here. This is sort of the very inception of the idea of a graph came from this sort of a model. So here we have what's called the 7 bridges of Königsberg. So Königsberg was the city. I forget what it's called now. It's not called Königsberg anymore. But in Königsberg, right, we have these different land masses that are connected with bridges. And this guy by the name of Leonhard Euler, who you might recognize that name from, say, the constant E, Euler's constant, or any number of great proofs that Euler did. He asked this question. He was living in Königsberg, and he asked this question: Can I travel along each bridge here, each of these 7 bridges, without repeating an edge, without repeating a bridge, without walking over the same bridge twice? Is there a way to do that? So he asked this question, and really this gave birth to graph theory. So the idea here is to think of each landmass as a vertex and the bridges as edges between those vertices. So here we have 2 bridges between these 2 landmasses. So I'll draw these 2 edges. Now I'll talk about this in a second. This isn't a simple graph as I have defined it earlier. And then this edge goes there, and that edge goes there, and this edge goes here. So see how we have 2 edges going between the same pair of vertices? In a graph, in our definition of graph in our book, this is not technically a graph. This is something called a multigraph, because what we have here are what's called parallel edges or multiple edges between the same pair of vertices. So this, strictly speaking, is not a graph according to our book, but of course there's lots of different definitions of graph, and this is sort of how graphs were first thought of. So the question was, now transferred to the language of graph theory, can we follow each edge exactly once without repeating an edge twice? And the solution to this was no, and that's really due to the fact that this vertex, we'll talk about this later when we talk about Eulerian graphs, but this vertex here has 5 edges coming off of it, and that's going to be an issue. How could we possibly travel all 5 of those bridges that come off of this landmass without repeating an edge, without crossing over the same bridge twice? It's impossible. So that's sort of the birth of graph theory, was this really innocent recreational type question about how these bridges are laid out. And really that's what graph theory was for, a couple hundred years there, was just these kind of recreational problems that could be asked about them. It wasn't really until we started developing the internet and all these different communication channels, telephones, electrical wires, these sorts of things, that graphs really became more important. So again, a graph, very abstract. What are the vertices? The vertices can be anything. So maybe the vertices are computers, and an edge exists between 2 vertices if there is some, let's say, a physical link between the 2 computers. And so that's the idea, is these vertices can be anything. Why not computers, and why not let the edges be connections between them? And so maybe we could think of edges between computers as there's some direct connection between them. Maybe we have an Ethernet cord between these 2 computers, something like that. Or edges could be intangible. So maybe these 2 computers are just connected on the internet in some way. Maybe there's a link between these 2 computers, something like that. They could be intangible or tangible. But then nevertheless, this is a big one, is thinking of computer networks. That's a huge application of graph theory. Here's an application from biology, where the vertices are animals. And now this is actually a directed graph. Notice we have arrows, so some notion of directionality to the relationships between 2 things. So we'll draw an arc from a vertex to another vertex if that animal is eaten by the other animal. So here there's an edge from the rabbits to the foxes, because foxes eat rabbits. And there's a directed edge, an arc, from plants to rabbits, because rabbits eat plants. So this is the idea of a food web. Typically these are directed graphs, because typically rabbits aren't going to eat foxes, but foxes eat rabbits. So there's a directionality here. Now, I went to a conference last summer about something called network science, and network science is graphs can be applied to basically any science. There were physicists there were biologists, there were anthropologists, there were computer scientists. any sort of science you can imagine, they have found a way to apply graphs to their subject and get great results. So I did see a lot of food webs there, and then they study these structural properties of that directed graph using the language of graph theory. Here is a monstrous graph. This one, each vertex is an airport, and an edge exists between two airports if there is a direct connection between those two airports. So if there's a flight from one airport to the other directly, then there is an edge between those two vertices. So, and this is just in the United States. You can imagine doing this in the whole world. This is a really big graph with lots and lots of edges. And in fact, this is, some people might think this is a small graph. So another example of an application of graph theory is to social networks. So think of Facebook. Think of the vertices of the Facebook graph as being people, and the edges, so there's an edge between two people if they are friends on Facebook. Now there are millions of users on Facebook, and along with that, billions of edges that are there. And so a Facebook graph is a very, very big graph. And so we'll want to develop tools for dealing with those really big graphs. And largely this is the topic of network science, of sort of applying statistical methods to these really big graphs that we can't apply the methods we're going to learn in this class to. So that's sort of a subject for a later class, are applying a lot of different statistical methods to these things to get information. So things like clustering. Can I identify clusters in my graph? This can be, applied to the Facebook graph in terms of a little friend network inside of the much bigger network. So there's lots of different applications. Again, high degree of abstraction leads to a high number of applications. And as we saw, we won't always just have simple graphs. We'll have to modify our definition of graph. And again, I'll talk about that at the end of this video of these different notions of graph. So a lot of times, a graph is defined not by just giving you the vertex set and the edge set, but rather telling you what the vertices are and then telling you some rule for how the vertices are adjacent to each other. So for example, let G be this graph with vertex set V, edge set E, where the vertex set is this one, 2, 3, 4, 6, 7, 8, 9, 10, 8, 9, 12, 18, 27. So that's my vertex set are these numbers. And I'll tell you that the vertex I is adjacent to the vertex J if I divides J or J divides I. So if one divides the other one, we'll draw an edge between those two vertices. All right, so let's draw this graph and use it as an example to talk about some more terms, specifically neighborhood and degrees. So I have, 11 vertices here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here's my graph. Let me write down. So I'm drawing this in a very specific way, and that's because I've already drawn this. And so I know how to make it sort of look nice, but maybe you don't know how to do that. It's okay to just throw down the vertices and start drawing edges between them. What is this one? I want this one to be 18, 9, 27, 3. All right, pardon me, I actually only had 10 vertices here. This one should go away. So sometimes, what's important is, again, the graph is just the vertex set and the edge set, which means a drawing, while it can define a graph, many drawings can define the same graph. So it doesn't matter where I'm placing these vertices and how I'm drawing the edges, so long as they go between the right vertices. There's lots of different drawings for the same graph. Okay, so let's start going through this. So how are these edges defined, right? As if one divides the other. So 2 divides 8, so we get an edge there. 4 divides 8, we get an edge there, and 2 divides 4. Notice 2 does not divide 7, nor does 4 or 8 divide 7, and so none of those are adjacent. 2 does divide 12, and 4 divides 12, so those are adjacent. 8 does not, though, so I won't draw an edge there. 2 divides 6, but 4 doesn't, and 8 doesn't, and certainly 12 doesn't. 6 divides 18. 4 doesn't, 2 does, 8 doesn't, 12 doesn't. 3 divides 18, 3 divides 6, 3 divides 9, and 3 divides 27. 9 divides 27, and 9 divides 18. Let's see, did I miss any? Yeah, I did. 6 divides 12, and 3 divides 12. Notice I often try and draw my edges as straight lines, but it's unimportant. We can draw curved lines as well. That's fine. I could even draw a bunch of squiggles or something like that, but it's best to try and keep it as simple as possible. Let's see, do I have any other divisors here that I missed? I don't know. Let me know if I do in the comments. I think this is good. Notice that 7 here it doesn't divide any of these other numbers. And so what we say here, 7 is an isolated vertex. In particular, its neighborhood is empty. So what's a neighborhood? A neighborhood of a vertex is the set of all those vertices it is adjacent to. And it's denoted with an n of that vertex. So here we can see that neighborhood of vertex 7 is empty. What other neighborhoods can we pick out, right? There's a neighborhood for every single vertex in this graph. Neighborhood of 3 is, so what are all the vertices 3 is adjacent to? Well, 3 is adjacent to 6, and 12, and 18, and 9, and 27. And so that's the neighborhood of 3, all those vertices that it's adjacent to. And we'll want to know how many vertices are in a particular vertex's neighborhood. That's called the degree of the graph. So the number of vertices in its neighborhood is the degree of that vertex. So for instance, 7 here, I said it's an isolated vertex. Another way to say that is it has degree 0. So degree we can also think of as the number of edges that are incident with that vertex. So here degree of vertex 7 is 0 because there's no vertices that are adjacent to it. There's no edges that are incident with it. Degree of 3, I like to just do D. We could also say deg, degree of 3. Those are two ways of writing this. Degree of 3 here is how many edges are incident with it. I can count them up, 1, 2, 3, 4, 5, also number of neighbors. So the degree of 3 is 5. So that's the idea of neighborhood and degree. When we have a graph like this, we might be interested in what's the smallest degree and what's the largest degree of any vertex in the graph. So this is the idea of minimum degree. Usually we use a delta. So delta of this graph, that's the smallest degree in the whole graph. So in this case, 7 had degree 0. There's no other vertices of degree 7. And so the smallest degree of the graph is 0. So that's delta, little delta of g. And I'll use capital delta of g for the maximum degree. Maximum degree, right? So we'll look at all the vertices and identify which one has the highest degree. So degree of 8 here is 1, 2. Degree of 4 is 3. Degree of 7 we already said was 0. Degree of 2, 1, 2, 3, 4, 5. It's degree 5, 1, 2, 3, 4. 1, 2, 3, 4, 5. For 3, we already counted that one. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2. So we've just looked at the degree of every single vertex in this graph. And if we pick out the biggest one, so 5, vertex 2 and vertex 3 both have degree 5, then that's the maximum degree. So big delta of g here is 5. I want you to notice something about how the degree of a vertex relates to the number of vertices, and that's what is the highest the maximum degree could possibly be. That is, what's the highest degree any vertex can have in a graph. And with this simple graphs that we're working with here, so no multiple edges between the same pair of vertices and no loops. So for instance, a vertex can't be adjacent to itself. We don't allow that. So in this case, the highest a degree can be is if that vertex is adjacent to every other vertex of the graph. And there are a total of, let's say, n vertices in a graph. So let's say this has, well, let's look at this specific example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've already counted this, right? So the cardinality of the vertex set is 10. So we say G has order 10. In general, the most a degree can be is one less than the order of the graph. So that is delta of G is between 0. It's possible we have an empty graph, so it's possible all vertices have degree 0. Between 0 and 1 less than the order of the graph. Less than or equal to. Less than or equal to. And same thing with the minimum degree. It's got to be somewhere between 0 and the order of the graph, and that's true just for the degree of any vertex. It has to be between 0 and 1 less than the order of the graph. Now, in the activity that goes along with this, you'll develop a connection between the sum of the degrees. So if I take all of these vertices, I don't know. Let's do it. So if I sum up the degrees of all these vertices. What do I get? 5, 10, 14, 18, 23, 27, 30, 32. I get 32. And notice how many edges are in this graph. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this 32 is 2 times 16, which is the size of the graph. That's not special to this graph. This will always happen. And why is, the proof of we call this the first theorem of graph theory. And in the proof, you can see why this is happening. And in the activity, I have you sort of discover this, try and discover this proof on your own. All right, I know this is a long video, bear with me. Another term here is regularity. This has to deal with degree. So sometimes a graph will have every vertex being the same degree. And so that's what we call R regular. So I'm going to draw a pretty famous graph here. This one's called the Peterson graph. And it's famous because it breaks a lot of conjectures, a lot of things that people think are true for all graphs. The Peterson graph serves as a counterexample. So if you're trying to come up with a counterexample, if there's some homework problem that says, oh, is this thing always true? Or come up with a counterexample that disproves the statement, this is a nice graph to look at because it breaks a lot of these things that seem like rules. It seems like they apply to everything, but they won't apply to the Peterson graph. It's very special. So one special property of the Peterson graph is that if I look at every vertex, you'll see that there are 3 incident edges with every vertex, or that the neighborhood of every vertex has 3 vertices in it. So this is the degree of every vertex, degree of V equals 3 for all V in V. When this happens, we say that it's 3 regular. So I should have called this, I'm going to call this P for Peterson. So P is 3 regular. It's a 3 regular graph. And that's just what we mean by regularity, is that every vertex has that same degree, 3. So in general, R regular, every vertex has degree R. All right, one last slide for other graph-like structures. So right with a simple graph, some people call these simple graphs, or they've even called Michigan graphs. We don't allow things like loops that go from so an edge going from a vertex to itself. So an edge like maybe this is vertex 3, an edge like 3, 3. Notice that would be an example of a multi-set. Normally sets don't contain multiples of any single element. And so that's why we call this we call this a pseudograph. At least our book calls this a pseudograph, is one with loops. A multigraph is one with multiple edges. So typically we don't allow loops in a graph, and typically we don't allow things like an edge going, or 2 edges going between the same pair of vertices. So something like, and in the bridges of Königsberg, we ran into that. That was a multigraph. So notice here, maybe this is vertex A and this is vertex B. The edge AB would show up twice in the edge set. And so again, typically the edge set is a set and won't allow multiples of this. But with a multigraph, we think of the edge set as a multi-set, and this is okay to do. Typically, we don't allow that. So a simple graph, we don't allow these multiple edges, but in a multi-graph, that's okay. Another thing we won't get to too much in this class is the idea of a directed graph, but likely you will work with these at some point, especially if you're in computer science, things like this, when you're dealing with data structures. Sometimes you'll want a directionality to your edges. And so let me draw arrows. So let's say this is vertex A, this is vertex B, and maybe we have vertex C down here. And maybe, I don't know, some other ones. And maybe it loops back around. We'll call these D and E. So vertex set is the same, it's just a set of vertices, but the edge set now is different. The edges aren't unordered sets anymore, they're ordered sets. And so this, we would specify an edge. These are typically called arcs when there's a directionality to them, and then we'll use our notation for ordered pairs like AB. And so we can say AB is an arc, CD is an arc. Notice that BD, even though there's an edge between them, it's not in the right direction. BD is not in the edge set here, but DB is. And in this case, we can even have like a multi-digraph where we have maybe some bidirectional edges like that. That's okay. So this is what's called a digraph, or directed. That's short for directed graph. And so sometimes the situation will call for a directionality on edges, like in the food web example we saw, and that's okay too. It's just not the same thing as a simple graph. So all these things have their place. There are times where you might want to use one, but for this class, we're going to stick mostly to just graphs. We'll encounter multigraphs a bit when we talk about Eulerian graphs. All right, that's it for this video. Hope you enjoyed it. Sorry it was a bit long. We'll talk some more about section 12.1 in the next one.